Welcome to our deep dive into multithreading in Java. In today's digital world, applications need to be fast, responsive, and capable of handling multiple tasks at once. Multithreading is the key to achieving this, especially in Java, where robust support for concurrent execution is built right into the language. Throughout this video, we'll explore how multithreading works, why it matters, and how you can leverage it to make your Java programs more efficient. We'll start by understanding the basics of CPU operations, then move through threads, processes, synchronization, and advanced concurrency tools. Let's begin our journey by looking at the CPU, the heart of every computer system. CPU, often called the brain of the computer, is responsible for executing instructions from programs. It performs arithmetic, logic control, and input-output operations. Modern CPUs are equipped with multiple cores, each capable of handling separate tasks. This means your computer can run several operations at once, such as browsing the web, playing music, and downloading files simultaneously. Understanding how the CPU manages these tasks is crucial to grasping multithreading. Next, we'll look at what a core is and how it enables parallel processing. Core is an individual processing unit within a CPU. Modern CPUs can have multiple cores, allowing them to perform multiple tasks simultaneously. For example, a quad-core processor can handle 4 tasks at once. This is why you can listen to music, browse the internet, and download files all at the same time. Each core can be assigned a different task, making the system more efficient than relying on a single core. This parallelism is foundational to multithreading, which we'll explore in detail soon. Program is a set of instructions written in a programming language that tells the computer how to perform a specific task. When you run a program, the operating system creates a process to manage its execution. For example, opening Microsoft Word turns it into a process. Each process is managed by the OS, which allocates resources and tracks its progress. Processes are the building blocks of multitasking, allowing multiple applications to run at once. Next, we'll see how threads fit into this picture. Thread is the smallest unit of execution within a process. While a process can have multiple threads, each thread runs independently but shares the same resources. For instance, a web browser like Chrome uses multiple threads for different tabs, making each tab responsive. Threads allow finer control over task execution and are essential for building responsive applications. Understanding threads is key to mastering multithreading in Java, which we'll discuss next. Multitasking allows an operating system to run multiple processes at the same time. On single-core CPUs, this is achieved through time sharing, where the CPU rapidly switches between tasks. On multi-core CPUs, true parallel execution occurs with tasks distributed across cores. The OS scheduler balances the load, ensuring efficient and responsive system performance. Multitasking utilizes the CPU's capabilities, assigning different tasks to different cores for maximum efficiency. Multithreading refers to the ability to execute multiple threads within a single process concurrently. For example, a web browser can have separate threads for rendering pages, running JavaScript, and managing user inputs. This makes the application more responsive and efficient. Multithreading breaks down tasks into smaller subtasks, allowing them to be processed simultaneously and making better use of the CPU's capabilities. Let's see how this works in single-core and multi-core systems. A single-core system, both threads and processes are managed by the OS scheduler using time slicing and context switching. This creates the illusion of simultaneous execution. In a multi-core system, threads and processes can run in true parallel on different cores. The OS scheduler distributes tasks across cores to optimize performance. Understanding these differences helps you design applications that scale efficiently across hardware. Time slicing divides CPU time into small intervals called time slices or quanta. The OS scheduler allocates these slices to different processes and threads, ensuring each gets a fair share of CPU time. This prevents any single process or thread from monopolizing the CPU, improving responsiveness and enabling concurrent execution. Time slicing is fundamental to multitasking and multithreading, especially on single-core systems. Context switching is the process of saving the state of a currently running process or thread and loading the state of the next one to be executed. When a process or thread's time slice expires, the OS scheduler performs a context switch, moving the CPU's focus to another process or thread. This allows multiple processes and threads to share the CPU, giving the appearance of simultaneous execution on single-core CPUs and improving parallelism on multi-core CPUs. While multitasking refers to running multiple applications, multithreading is more granular, dealing with multiple threads within the same application or process. Multithreading enhances multitasking by breaking tasks into smaller threads, which can be managed concurrently. This distinction is important for designing efficient Java applications, as multithreading allows for better resource utilization and responsiveness. Java provides robust support for multithreading, allowing developers to create applications that perform multiple tasks simultaneously. Java's multithreading capabilities are part of the Java Lang package, making it easy to implement concurrent execution. In single-core environments, Java's multithreading is managed by the JVM and OS, which switch between threads to give the illusion of concurrency. In multi-core environments, Java can distribute threads across cores for true parallel execution. Java, you can create threads by extending the thread class or implementing the runnable interface. When a Java program starts, the main thread begins running immediately, executing the main method. To create additional threads, you can extend thread and override the run method or implement runnable and pass it to a thread object. Both approaches allow you to define custom thread behavior and start concurrent execution. Create a new thread by extending the thread class. You define a new class that extends thread and override the run method. The start method is called to initiate the thread. This approach is straightforward and allows direct control over thread behavior. However, it limits inheritance as your class can only extend thread. Use this method when you need to override thread methods or require direct thread control. Alternatively, you can implement the runnable interface to create threads. This allows your class to extend another class if needed, providing more flexibility. You override the run method, then create a thread object by passing an instance of your runnable class. The start method is called on the thread object to initiate execution. This approach is preferred when you want to separate the task from the thread itself. Lifecycle of a thread in Java consists of several states: new, runnable, running, blocked, waiting, and terminated. A thread starts in the new state, becomes runnable after start is called, enters running when executing, moves to blocked waiting when waiting for resources, and finally reaches terminated after finishing execution. Understanding these states helps you manage thread behavior and troubleshoot issues in concurrent application. Choosing between runnable and thread depends on your needs. Use runnable when you want to separate the task from the thread, allowing your class to extend another class. Extend thread if you need to override thread methods or require direct control over the thread. Runnable is generally preferred for flexibility and cleaner design, while thread is useful for specialized thread behavior. Java's thread class provides several important methods. Start begins execution, run is the entry point, sleep pauses execution, join waits for a thread to finish, set priority changes thread priority, interrupt interrupts the thread, yield suggests pausing for other threads, and set daemon marks a thread as a daemon. Each method serves a specific purpose in managing thread behavior and coordination. Read priority determines the order in which threads are scheduled for execution. You can set priority using set priority with values ranging from thread min priority 1 to thread max priority 10. Higher priority threads are more likely to be executed first, but actual scheduling depends on the JVM and OS. Managing thread priority helps optimize performance and responsiveness in concurrent application. Interrupt method allows you to interrupt a thread, especially if it's blocked in wait, sleep, or join. This throws an interrupted exception, enabling you to handle interruptions gracefully. The yield method suggests that the current thread pause execution to let other threads run. Yield is a hint to the scheduler and may not always result in a pause. These methods help manage thread coordination and responsiveness. Daemon threads are background threads that run in support of user threads. When the JVM exits, all daemon threads are terminated. You can mark a thread as a daemon using set daemon true. Daemon threads are useful for tasks like garbage collection or background monitoring. User threads, on the other hand, keep the JVM running until they finish execution. Synchronization is essential when multiple threads access shared resources. Without synchronization, race conditions can occur, leading to inconsistent results. By using the synchronized keyword, you ensure that only one thread can access a method or block at a time. This prevents race conditions and ensures thread safety. Let's look at an example with a shared counter. Consider two threads incrementing the same counter. Without synchronization, the output may not be as expected due to race conditions. Both threads might read the same value, increment it, and write it back, losing one increment. By synchronizing the increment method, you ensure only one thread can execute it at a time, consistently producing the correct result. Synchronized keyword provides basic thread safety but has limitations. It locks the entire method or block, which can lead to performance issues, and lacks try-lock mechanisms. Explicit locks like those provided by the lock interface offer finer control, try-lock capabilities, and support for multiple condition variables. This makes them more flexible and powerful for complex concurrency scenarios. Reentrant lock allows a thread to acquire the same lock multiple times without causing a deadlock. If a thread already holds the lock, it can reenter without being blocked. The reentrant lock class provides this functionality, offering try-locking, timed locking, and multiple condition variables. This is useful for advanced thread coordination and avoiding deadlocks. Reentrant lock provides several methods. Lock acquires the lock, try-lock attempts to acquire without waiting, try-lock with timeout waits for a specified time, unlock releases the lock, and lock interruptibly acquires the lock unless interrupted. These methods allow for flexible and safe thread coordination, preventing deadlocks and improving performance. Read-write lock allows multiple threads to read shared data simultaneously while restricting write access to a single thread. The reentrant read-write lock class optimizes performance in scenarios with frequent reads and infrequent writes. Multiple readers can acquire the read lock without blocking each other, but writers must acquire the write lock for exclusive access. This prevents data inconsistency and improves efficiency. Fairness in locks refers to the order in which threads acquire a lock. A fair lock ensures threads acquire the lock in the order they requested it, preventing thread starvation. However, fairness can lead to lower throughput due to the overhead of maintaining order. Non-fair locks allow threads to cut in line, offering better performance but risking indefinite waiting for some threads. Deadlock occurs when two or more threads are blocked forever, each waiting for the other to release a resource. This typically happens when threads hold locks on resources and request additional locks held by other threads. Deadlocks can severely impact system performance and are challenging to debug and resolve. Avoiding deadlocks requires careful design and coordination. Threads often need to communicate and coordinate actions. Java provides mechanisms like wait and notify for thread communication. For example, a producer thread can produce data and notify a consumer thread to consume it. Synchronization ensures that threads wait for the right conditions before proceeding, enabling safe and efficient communication between threads. The producer-consumer model: one thread produces data while another consumes it. Synchronization ensures that the producer waits if data is already available and the consumer waits if no data is present. This coordination prevents race conditions and ensures efficient data exchange between threads. Java's synchronized methods and wait notify mechanisms make this possible. Executors framework introduced in Java 5 simplifies concurrent application development by abstracting thread management. It helps avoid manual thread creation, manages resources, scales efficiently, reuses threads, and handles errors. Executors provide thread pools and scheduling, making it easier to build scalable and robust Java applications. Executor service allows you to manage a pool of threads and submit tasks for execution. For example, you can create a fixed thread pool and submit tasks like calculating factorials. The executor manages thread lifecycle, ensuring efficient resource use. After submitting tasks, you can shut down the executor and wait for completion. This approach streamlines concurrent task execution. Future and callable interfaces enable asynchronous task execution and result retrieval. You can submit a callable task to an executor service and get a future object. Calling future.get blocks until the task completes, allowing you to retrieve the result. This mechanism is useful for managing long-running tasks and coordinating their completion. Atomic classes like atomic integer provide thread-safe operations without explicit synchronization. For example, atomic integer's increment_get method ensures atomic updates, preventing race conditions. These classes are useful for counters and other shared variables in concurrent applications, offering performance and safety. Volatile keyword ensures visibility of changes to variables across threads. When a variable is declared volatile, updates are immediately visible to other threads. This is useful for flags and simple state variables, ensuring that threads don't cache outdated values. Volatile is not a substitute for synchronization but helps with visibility in specific scenarios. Countdown latch is a synchronization aid that allows one or more threads to wait until a set of operations completes. You initialize the latch with a count, and threads call countdown as they finish. Other threads call await to wait for the count to reach 0. This is useful for coordinating tasks and ensuring proper sequencing in concurrent applications. Cyclic barrier is another synchronization tool that allows a set of threads to wait for each other to reach a common barrier point. Once all threads arrive, the barrier is released and they proceed. This is useful for coordinating phases of computation, such as initializing subsystems before starting the main system. Cyclic barrier enables efficient group synchronization. Thread communication is vital for building responsive and efficient applications. Java provides tools like wait, notify, countdown latch, and cyclic barrier to coordinate actions between threads. Proper communication prevents race conditions, deadlocks, and ensures tasks are completed in the right order. Mastering these tools is essential for advanced Java development. Java's concurrency package offers advanced tools for managing threads and synchronization. Executors, future, atomic classes, and synchronization aids like countdown latch and cyclic barrier provide robust solutions for complex concurrency scenarios. Leveraging these tools helps you build scalable, efficient, and safe applications that make full use of modern hardware. Multithreading is used in real-world applications like web servers, database systems, and multimedia processing. It enables responsive user interfaces, efficient background processing, and scalable server architectures. By mastering multithreading in Java, you can build applications that handle multiple tasks smoothly and deliver a better user experience. While multithreading offers many benefits, it also introduces challenges like race conditions, deadlocks, and thread starvation. Careful design, proper synchronization, and use of advanced concurrency tools are essential to avoid these pitfalls. Testing and debugging concurrent applications require special attention to ensure reliability and performance. Let's recap the key concepts covered in this video. CPU cores enable parallel processing, threads are the smallest execution units, synchronization prevents race conditions, locks and advanced tools manage thread coordination, and Java's concurrency package provides robust solutions. Understanding these concepts is crucial for building efficient and scalable Java applications. Let's take a visual recap of multithreading in Java. From CPU cores to thread lifecycle, synchronization, locks, and advanced concurrency tools, each component plays a vital role in building responsive and efficient applications. These visuals help reinforce the concepts and show how they fit together in real-world scenarios. Congratulations on completing this journey through multithreading in Java. You now have a solid understanding of how threads, synchronization, locks, and advanced concurrency tools work together to build efficient applications. As you continue learning, experiment with these concepts in your own projects and explore Java's concurrency package further. With practice, you'll be able to create scalable, responsive, and robust Java programs that harness the full power of modern CPU.